be no water flow through some of the tubes. The result of this reduction in heat exchange will be that the condenser is less effective and the turbine back pressure increases. The siphon connection prevents this from happening by drawing off the air at the top of the water box and piping this into a vacuum tank. The vacuum in the tank is maintained at about 25 inches of mercury by small vacuum pumps that are intermittently operated. A water level sensor in the water box operates a control valve on the siphon connection. When the level falls below a set level, the valve opens and air is drawn out, allowing the water level to rise. When the level raises to fill the water box, the control valve closes to the steam space of the condenser instead of steam leaking out. Also, some incondensable gases, such as oxygen and carbon dioxide, may be released from the steam as it condenses. There is a tendency for these gases, plus any small amount of leakage air, to accumulate inside the steam space and eventually cause the back pressure to rise, reducing turbine efficiency. In order to remove air and gases from the steam space, vacuum devices are fitted, such as a steam ejector and a vacuum pump. This air removal equipment is connected to a specific location in the condenser known as the air box. In this area, additional cooling tubes are concentrated to ensure that the steam condenses and only air and gases are removed. In many plants, the discharge from the vacuum equipment is monitored to provide a measure of air leakage into the condenser. During normal operation, this air leakage should be quite small. In fact, a good test of this during operation is to shut down the vacuum pump or steam ejector and observe the rate at which the back pressure increases. This should be quite slow, say 1 inch of mercury in about 30 minutes. Compare this with the change which would take place if all of the circulating water flow were to cease, perhaps due to a trip of the circulating water pumps. In this case, with no condensing taking place at all, the back pressure would rise immediately, and the turbine would have to be behind. The condenser and the turbine are full of air. In order to remove this air, the vacuum pump or steam ejector must be placed in service and so pull a vacuum inside the unit. Let's see how the steam ejector works. This functions on the principle of the Venturi nozzle like this. When high-velocity steam passes through this nozzle, it creates a vacuum at this convergent point. This is the point which is connected to the air box in the condenser. The air enters the nozzle and is mixed with the steam passing through. On a startup ejector, also known as a hogging ejector, this mixture is discharged to atmosphere. However, the requirement for air removal when the turbine is in service is much less. Therefore, the on-load ejector uses smaller nozzles and has some heat and steam recovery. As before, air is drawn from the condenser by the primary ejector, and the air and steam mixture discharges into a heat exchanger to condense the steam. The cooling medium is usually condensate, so all of the heat is retained within the cycle from the intercooler. The air is now drawn into a second